How do we determine who's being oxidized and who's being reduced in a reaction where it's not so obvious? Well, of course, we're going to use oxidation numbers, and that's what today's talk is all about. Let's get right to it and talk about what an oxidation number is. An oxidation number is an arbitrary way of keeping track of electrons that are being lost or gained. And we did talk about that before. If you lose electrons, you are being oxidized, and you gain electrons, you're being reduced. And here's the reasoning behind that. With oxidation numbers, reduction means that we take an oxidation number and we reduce it. A decrease in oxidation number is called reduction, and an increase in oxidation number is, sorry, I made a little typo there. An increase in oxidation number is going to be oxidation. So, okay, we have rules for oxidation numbers, and we follow these rules so that we can figure out the oxidation number of any either element, compound, or polyatomic ion. So our first rule for oxidation numbers is that any elemental form of an atom or element has an oxidation number of 0. And so what that means is, I'll give you a couple examples here. Let's say hydrogen gas. Hydrogen gas is elemental. This is how you will find hydrogen at 1 atmosphere, 25 degrees Celsius. And so we would say that each hydrogen has an oxidation number equal to 0. Okay. Same thing goes for like a solid phosphorus, which is usually written as P4. We would say that each phosphorus has an oxidation number equal to 0 as well. Okay. Monatomic ions, they're typically whatever charge they have, that's going to be their oxidation number. So if we were looking at a monatomic ion such as the potassium ion, we would say it has a +1 oxidation. If we were looking at, let's say, the sulfide ion, we would say it has a -2 for its oxidation number. There's some tricks that go on along with some of the metals. Of course, some of these nonmetals. Now, these nonmetals do follow the same rule, just like the monatomic ions. For example, if you're dealing with the oxide ion, we will say that that's going to be an oxidation number of -2. But we can have the peroxide ion, and this is the peroxide ion. And so one thing to keep in mind is in the peroxide ion, you have diatomic oxygen with a 2- charge. So we would say each oxygen will have a -1 oxidation number. Okay. Hydrogen, also considered mostly nonmetal. H1+ is the typical form of a hydrogen ion, and that's going to have an oxidation number of +1. But we do have what's called a hydride, and this is when hydrogen has a 1- charge. It's called a hydride. And in this case, the oxidation number is going to be -1 for hydrates. This is when hydrogen bonds to metals. So when hydrogen bonds to metals, we have a -1 oxidation number. Now, what does this have to do with anything? Well, first off, we say that in a neutral compound, the sum of the oxidation numbers is going to be 0 for neutral compounds. The sum is going to be 0. So this is what I mean by this, and this will give you an example. Let me scooch this down a little bit here. Let's say an example of so we want to find the oxidation number for carbon in the CO2 molecule. Okay, so as we said, the sum of the oxidation numbers is going to be 0. So what we're going to do is we're going to set this equal to 0 because the sum is going to be equal to 0. And then we're going to say, okay, sum is adding, so we have carbon plus, for the oxygen, we have 2 oxygens, which we're multiplying by oxygen's oxidation number. Well, oxygen's oxidation number is typically a -2. So we're going to have carbon plus -4 is equal to 0. Carbon is equal to 0. So we would say the oxidation number of carbon in this case, excuse me, that was incorrect. We're going to solve this for carbon, is going to be +4. So in this case, carbon would be +4. That would be the oxidation number of carbon within that molecule. Okay, now For the next one, the sum of oxidations for polyatomic compounds equals the charge of that ion. So, give you an example here of what we're talking about. Let's say find the oxidation number of sulfur in the sulfate ion. Find the oxidation number of sulfur in the sulfate ion. So in a charged particle, we have a -2 charge. So the sum of the oxidation numbers is going to equal the charge of the ion. So we're going to set this equal to -2 because sulfate has a 2- charge. And so it's going to be sulfur plus, this is for oxygen, we have 4 oxygens. You can see 4 oxygens right there. And we're going to multiply that by the oxidation number of oxygen. In this case, it's -2. -2. And so we're going to have sulfur plus -8 is equal to -2. Solve it for sulfur. Sulfur is equal to +6. And there's our answer. So we'd say the oxidation number in this case of sulfur is +6. So let's talk about application of this. And we've talked about before how we determine using a half reaction whether somebody's being oxidized or reduced, whether being losing or gaining electrons. But sometimes it's not so easy to identify that. So here's an example of it. Which reaction is oxidized and which is reduced when solid nickel is reacted with chlorine gas to produce nickel 2 chloride gas? Okay, so we're going to write a complete ionic equation or complete molecular equation for this. So we have nickel solid plus chlorine gas. Chlorine gas is diatomic, and that's going to produce nickel 2 chloride gas. Okay, so the question is which reactant's being oxidized, which reactant's being reduced, and the only way to really tell on this is to use oxidation numbers. And so nickel in its solid form is an elemental form, so that's an oxidation number of 0. Chlorine gas, that's how it exists in nature, that's its elemental form, it's also a 0. Now we go over here and look at the nickel 2 chloride. So nickel, this is an ionic compound, so the nickel is going to have a +2 oxidation, and each of the chlorines typically have a 1- charge, so each of the 2 chlorines is going to be N-1, and that accounts for the 2 chlorines that we have, so -1, -1. Okay, so let's look just at the nickel here. So going from nickel here to there, what's happening is we are increasing our oxidation number, and that's oxidation. When you increase your oxidation number, that's oxidation. And then if we look here from chlorine, Cl2, to there, to the Cl2, we are decreasing. We're going from a 0 decreasing down to a -1. So this is a decrease in oxidation number, which equals reduction. So we would say that the nickel is being oxidized and the chlorine gas is being reduced. And that's why we use oxidation numbers on reactions that sometimes it's not obvious where the electrons are being transferred from place to place.